Yeah, all that background. So our last two lectures this week, and no written work homework for this unit. Instead, what I'm hoping is that we have more time on Thursday to practice mechanisms together. Because you will have a mechanism on the unit test this weekend. So I'm hoping we can do more practice in person on Thursday to set you up for success. I recognize for those of us that don't attend the class in person, that means less targeted feedback on how your mechanisms are going. But let's be honest, no shame. Mechanisms usually aren't turned in time for me to give feedback before you guys go and do your unit tests. So it hasn't been super helpful throughout the semester anyways. So a few new reactions to learn, and those reactions have been posted to Canvas. I'm going to put these up on the screen for us. We're going to start with our Aldol addition reaction. Can anybody remind me what an addition reaction entails? Centinaura? Removes a pi bond. And remove is an interesting way to say it, right? Because when you look at the structure, you do say there's a pi bond here, there's not a pi bond here, pi bond has been removed. But we're not really like taking something out, right? Which is why the reaction is called addition. So I like to say consume a pi bond. We consume a pi bond by adding two groups across it. We've done things like alkene addition, alkyne addition, and acyl addition. Now we're doing aldol addition. There is reason to believe that the term aldol actually is a shortening of the word aldehyde alcohol. So this is not somebody's name, even though it kind of sounds like it could be someone's name. Nope, I didn't ask the guy. Well, I didn't ask the guys that asked the guy. So aldol alcohol, which actually gives you an indicator as to what reaction forms. So we're going to be starting with this aldehyde that's pointed to the right. I want you to recognize that this says 2x. That means we're looking at two equivalences. What I'm actually going to do here is I'm going to draw the second equivalence in a different color. Our first reaction here, what we need is basic conditions, sodium hydroxide. We recognize that aldehydes with a base can actually do a few things. It can give us acyl addition. That hydroxide can attack the carbonyl and give us a diol, a geminal diol. That is a possibility of what goes on when this reaction happens. But other things also happen. The alpha hydrogen gets eliminated and an enolate forms. Enolates are nucleophiles and carbonyls are electrophiles. So I'm going to be labeling in blue that this carbon will become a nucleophile. Now that's just one molecule out of a reaction that probably contains billions of molecules, which means I am creating nucleophiles still in the presence of electrophiles. And specifically, the electrophilic character is at that carbonyl carbon. So I want to point out, I'm saying nucleophile at the alpha carbon. It's not a nucleophile as drawn. It becomes a nucleophile after that deprotonation. And it's in the presence of electrophiles. Nucleophile attacks electrophile. That's going to give us acyl addition. I'm going to draw the newly formed bond in green so that we can distinguish what was a part of the original structure? What was a part of the original two structures, and what is newly formed because of this reaction? Can you tell me how the base serves in this reaction? What role does sodium hydroxide play in this reaction, given that this is the product that forms? So it works as a base, it deprotonates the alpha carbon. It serves as a catalyst. Hydroxide loses a hydrogen? Yeah. Hydroxide? Hydroxide as a base might gain a hydrogen because it's taking a hydrogen, which I think is the opposite of losing a hydrogen. You okay? Yep. Do you want to clarify how you know that hydroxide serves as a catalyst?
Or I guess is that H goes to the O? No. And H gets moved on to the carbonyl oxygen. That H gets kicked off.
Actually, I'm going to argue that this aldehyde H does not get kicked off. It just becomes assumed. And to be fair, I could have assumed it from the very beginning. We don't have to show that aldehyde H. We have to know that it's there. What's interesting, though, is we went from sp2 to sp3, so I didn't show that H, but let's show it, because this is a good clarifier. The aldehyde hydrogen is not leaving. Hydrogens in general are bad leaving groups from carbons. They certainly don't take electrons with it. If they can have electrons, they can be taken when electrons are given, but they don't take electrons with it. So there is another modification I want to make to this final structure in terms of color, and that actually has to do with this hydrogen. That OH that's in orange did not come from this equivalence. It couldn't have. Look, CH3 in orange, CH3 in orange. Aldehyde H becomes an sp3H, and then the CO, CO. So where did that hydrogen come from? No. Sodium hydroxide as a base wants to take hydrogens. It definitely doesn't want to give away its hydrogen, but I like the thought. Comes from the other CH3, which becomes a CH2. CH3 becomes CH2. Where did that H go? And to be fair, it is hydroxide that takes that hydrogen, becomes water, the conjugate acid, and then water gets deprotonated by this oxygen. So hydroxide is facilitating the proton transfer. Hydroxide is taking an alpha hydrogen and then later giving it back here. So this is base catalyzed. We don't have to write catalytic, but if you run this, you don't need a stoichiometric amount. You don't need 1 mole of aldehyde and 1 mole of hydroxide, because that hydroxide is reproduced at the end of every step. Okay, so the colors I know can be a little bit confusing, so I want to demonstrate it just one more time and show you how you can take the starting materials and show the prediction of the products. What I like to do is set my nucleophile next to my electrophile. And this time, I think I'll leave off the hydrogens because we don't need to show them. Can get in the way a little bit. I'm setting my nucleophile next to my electrophile. I'm going to form a bond between my nucleophile and my electrophile, which means I break open the CO double bond, giving me an OH. Or in other words, in all one color,
how does the sodium hydroxide form the bond and why it's bond?
Good question. Actually, it's the nucleophile that forms the bond. But I can see, based on my color coding, why you would think sodium hydroxide did that. So maybe it would be more helpful to show the new bond that forms as this black color. Sodium hydroxide is in a way facilitating all of this, but it itself is not causing the new bond. Good question. What is the functional group here? How could we describe that? A di what? It's actually not a dioxy. Oxy, not a good substituent name. This could be a oxo group. This could be a hydroxyl group or a hydroxy, but not dioxy. We have two oxygens, but can we be more specific about what functional groups those oxygens are and how they're related to each other in the structure? This is an aldol. That's a very astute observation. Notice how I have an aldehyde alcohol, which is why we call it the aldol addition. But I actually introduced you guys to this functional group at the start of this unit amongst a number of other functional groups.
Those happen at the same time. One attacks one attacks the other.
All that once? No. First the enolate forms, then the enolate attacks.
The OH onto that carbon.
We'll look at the mechanism.
Oh, we're doing.
Yeah. Maybe not today, but we'll look at the mechanism for this reaction. How about this? What's the priority functional group? And then the less priority functional group would be the alcohol. How is the alcohol related in the structure to the aldehyde? Beta. So we can call it a beta hydroxy, not a ketone, aldehyde. Or generically, a beta hydroxy carbonyl.
Oh, that's just the group.
Aldol addition forms a beta hydroxy carbonyl. It does not have to happen. It does not have to happen with an aldehyde. Ketones also give aldol addition. So it's kind of like when we talked about acetals. Acetals, remember, are the gem diethers, the protecting group of an aldehyde, if you will. And acetals kind of have this name that comes from aldehyde, and yet we can apply acetals to ketones as well. So aldol also applies to ketones. It does not have to be just an aldehyde. We'll look at more examples where we have ketones as well. Aldol addition. That's it. That's the aldol addition. It gives a beta hydroxy carbonyl. Let's now take this to the aldol condensation. Unfortunately, the aldol condensation does not give an aldehyde alcohol. So now, again, we have kind of this misnomer with the name. It might as well just be a dead guy's name because it doesn't really tell you the product that forms. Once again, I'm going to show you the two equivalences in two different colors so that we can keep track of how these structures are reacting. And this time we're going to use sodium hydroxide and heat, which is to say the same reagent that gives you aldol addition can also give you aldol condensation. Typically, you just heat it up a little bit more to drive it to completion, or you can add an excess amount of base, which means when I ask you to do these type of problems, I do not leave it to you to guess, is he trying to get the aldol addition or is he trying to get the aldol condensation? I'm very explicit. Show me the aldol addition product that forms. Show me the aldol condensation product that forms. All you need to do is be able to distinguish what those words mean. You don't have to guess what condition am I actually giving here. Condensation means what? Okay, well, I mean, a gas turns into a liquid, condenses. In this context, we're going to be saying that we condense out a molecule of water. We will create a separate molecule. Here is the product that we get from this aldol addition reaction. And once again, I'm going to show the new bonds that form in black. And then here's a byproduct that forms. This gives us plus that's right. Just drive this further. What am I missing? I already did say it. Water. Where did the H's come from? I'll give you a hint. Hydroxide is another base. So sodium hydroxide here is a catalyst. Sodium hydroxide is still serving as a catalyst, which means sodium hydroxide is not responsible for that byproduct there. Not the H on the O one. Not the H on the orange one. The O on the orange one. The blue structure has lost 2 hydrogens. It went from a CH3 to a CH. 2 hydrogens missing. The orange equivalent has only lost its oxygen. So we've lost H2 and O. Okay, but I will admit this is a bit of a lie. In reality, we have formed an equivalence of water from hydroxide deprotonating, that alpha position. And then that actually happens twice. We'll look at it. There's a lot of proton transferring going on. I think the most useful way to think about this is your nucleophile needs to lose both of its alpha carbons. That means that we're actually forming that nucleophile twice. And then the oxygen also gets kicked off. We'll look at the mechanism to show how that happens. One more time with this process of how do you form it. This is one way to see the structure. You can kind of see how the bond line of the second equivalence stays the same, but I just form a double bond between nucleophile and electrophile. There's another way that you can predict these. Once again, I like to line up my nucleophile and my electrophile based on where they're going to react. But this time, I'm actually just going to substitute the CH3 and the O. I'm going to leave that double bond there, which means that drawn all in one color, I can draw my product like this. That's the same structure. It's just in a different conformation. It's rotated around one of its sigma bonds. Same structure. What is the functionality formed in this product? Aldol condensation gives aldehyde and alkene. Can we describe how closely they're related in the structure? So we could say alpha alkene carbonyl. A lot of times though, we'll actually say that it's an alpha beta unsaturated. That's our way of saying that it's an alkene carbonyl. It's a carbonyl whose alpha and beta positions have been unsaturated. One other way that we can say this, do you guys remember the other name for this functional group? No. It actually it highlights the molecular orbital theory. It highlights the resonance between the four positions. We call this a conjugated carbonyl. Because that alkene, being at alpha and beta, means that it is conjugated to that product. All right, the last reaction that's on that first flow chart is actually just taking two equivalences and reacting it with H3O+, which only gives the aldol condensation product. The aldol addition product is an intermediate in the formation of the aldol condensation product. So first, we form a beta hydroxycarbonyl, then those react to give a alpha beta unsaturated carbonyl. Yeah, there's something about the beta hydroxycarbonyl, which in acidic conditions is too reactive. In acidic conditions, this reacts even faster. The OH gets protonated and becomes a good leaving group, which leaves a carbocation at this position, which forces the alpha carbon to be deprotonated and form an alkene. So in acidic conditions, the aldol addition product is too reactive, and it's driven towards the condensation product. In basic conditions, you can control the energy of the reaction and isolate the aldol addition intermediate. Are you guys all right if I erase this first page so we can do some practice problems with this? Because now I want you guys to see aldol addition and aldol condensation, but not just with aldehydes. I want you to practice with ketones as well. So show me the aldol addition product when two equivalences of this ketone reacts with sodium hydroxide as a catalyst. And show me the aldol condensation when this ketone, two equivalences of this ketone, act with sodium hydroxide. I do try my best to always put two equivalences. It's not always explicitly said, though. And to be fair, I do want you to have the skill of recognizing I have a carbonyl and I'm expected to do aldol addition or aldol condensation. I will need one equivalence to be a nucleophile, and one equivalence to be an electrophile. Even if it doesn't explicitly say two equivalences, you should assume two equivalences. And some students will say, how am I supposed to know that there's two equivalences if it doesn't say that there are two equivalences? And the answer is, if it's just one chemical, use up half of it as the nucleophile and use up the other half as the electrophile. You can't add two equivalences of a reaction that has one reactant. It's gonna look funky. That's okay. If it helps, map your carbons. Perfect. Funky, right? You got it. Think about what carbon is attacking what carbon. Let that lead you on how you map. Close. Getting close. Oh, here's a tip on how you can map. You know that you're forming a beta hydroxycarbonyl, so label alpha and label beta on the starting materials, and then redraw those and make sure that you form a bond between alpha and beta. If you're forming a alpha-beta unsaturated carbonyl, make sure that you draw, label alpha, label beta, and draw bonds between them. Good. 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 Really close. But this would be a gamma hydroxycarbonyl, alpha, beta, gamma. Instead, I actually want this position to be, yeah? Let me see it. That's it. Funky looking, right?
That's very funky.
Yeah. But you've labeled alpha, you labeled beta, you've made sure beta is a hydroxy group.
So I have beta right being there?
No, this is alpha to the carbonyl,
Mm-hmm.
which means now this is beta. Carbonyl, alpha, beta.
Oh.
You're not wrong that well, no. That would have been originally an alpha position because this OH used to be a carbonyl.
Okay, I see. So is it still considered alpha to this, but it's beta to this one?
That actually, this is the original carbonyl carbon,
mm-hmm.
which is now a beta position to this carbonyl.
Okay.
Yep.
Okay.
That's actually the tip. I'm gonna have you guys write that down in a minute.
That's confusing because here beta is there.
That's correct. And beta is still there. Beta is alpha, sorry, carbonyl, alpha, beta.
Mm-hmm.
That position is still beta to the carbonyl, but now I have a new beta position as well.
Okay.
Yep. I want you to recognize the beta position in the product was what in the starting material? The new beta. That's right. That's right. That's right. The new beta carbon in the product, the beta carbon of the new functional group was a carbonyl carbon, was the reactive carbon. Nailed it. Oh, I think you lost the carbon on the bottom chain.
Oh, yeah.
Yes, got it. Yep.
Just to clarify, so it's only the alpha carbons that would react, right? And as long as you can take away two carbons.
As long as you can take away 2 hydrogens, you're good.
Hydrogens, yeah.
Yep.
Okay.
I mean, in a way, well, this is not alpha,
Oh,
right?
yeah.
Good. And then kind of the same thing down here. In a way, the carbonyl carbon is also reacting. You've got one equivalence where the alpha carbon is reacting because its conjugate base has resonance with the carbonyl. And then you've got the second equivalence that is reactive at the carbonyl as an electrophile.
Oh, okay.
Yeah.
So
like this alpha attacked a carbonyl, and now that carbonyl is beta to this carbonyl. Your carbonyl carbon became a beta carbon.
Oh, okay.
Yeah?
Yeah.
That's how I want you to identify it. And I'll write that out in a little bit. Do you have your top one? Perfect. That's it. Did you try the bottom one? Why don't you take a stab at that one? So here's a carbonyl. Here's its alpha carbon. Here's its beta carbon, which means it's not alpha beta unsaturated. It's actually beta gamma unsaturated. The other problem then is, so its alpha carbon should be the one engaging. That beta carbon should stay a CH3.
Oh, you're right. Okay.
And this carbon chain changed completely.
Also still
There
have
were 5 carbons here, and you brought it down to 4. And for whatever reason, one of the methyl groups must have been reactive and not the carbonyl carbon. Take that example I gave you up there and line up the alpha carbon with the carbonyl and just join the 2 structures as kind of a shortcut. Yeah? Yep. You got it. Still going to have a ring. In fact, you're going to have 2 rings. You're going to have a ring that attacks a ring, and so those rings will be bonded to each other now. Yep.
Sorry, I might have missed this, but what happens to the oxygen?
Good question. It leaves as water.
Oh, okay.
Yep.
So it just gets protonated, and then it becomes a good leaving group.
That's right. That's exactly it. Good. Good. You've got your alpha beta swapped though. This is alpha to the carbonyl, and this is beta to the carbonyl. Yeah, down here as well. This is the alpha carbon. Carbonyl carbon.
Okay.
Carbonyl is the reference point.
Yeah.
Carbonyl is
And
not
then they
alpha.
end up as
Yep. So this is a beta hydroxy carbonyl, alpha beta.
Got it. Okay. Thank you.
Yep.
Thank you.
All right, are you guys ready?
Yep.
So, paying attention to alpha and beta. Here's what I want. I want you guys to write this down because this is a useful tip. The electrophile carbonyl carbon becomes, that's not a good arrow for it because that usually means comes from, becomes the new beta carbon. That's because the alpha carbon of one equivalence becomes a nucleophile. Once the nucleophile attacks the carbonyl carbon, alpha is now bonded to a new beta. So the carbonyl carbon that gets attacked is now a beta carbon. Maddie, I'm sorry you missed the first board. So there was some intro stuff. Yeah. Yep. No, I erased it. I'm sorry. Okay. All right, so what I'm going to do here is I'm going to copy over 2 equivalences of my starting material. And I'm going to kind of offset them. That aldehyde example was a very nice example. Congratulations, I did not give you a nice example here. I'm going to label my alpha and beta. It doesn't matter which equivalence attacks which equivalence. And I noticed some of you have different things attacking different directions. So bear with me and if mine looks like a mirror of yours. This is my alpha carbon for my carbonyl. I'm going to call this the nucleophile, which means that this equivalence is the electrophile, and alpha will now attack a new beta carbon. That beta carbon will have to lose one of its bonds. That's where my beta hydroxy carbonyl comes from. Pretty? No. So let me redraw it. Alpha attacks beta, and beta is a part of this larger ringed system. Still not the prettiest, I'll give you that, but it's a little bit prettier. It's really not that pretty. It never got better, did it? Once again, carbonyl, alpha, beta. The electrophile carbonyl becomes the beta carbon. That's how I want you to track this. That means that you're now able to retrosynthesize as well. Identify your beta carbon, cut the alpha beta bond. You now have your electrophile carbonyl again. Same thing for this next one. I'm going to take two equivalences of this, and I'm going to set them up such that the alpha carbon lines up with the carbonyl. And then the only thing that I'm going to do is erase the oxygen and just make that double bond. Pretty? Not always. So now that we know what that structure looks like, we can go back in and redraw it. It wouldn't have mattered if you went to the other side because this is symmetric. Go ahead. That's a conformation of the structure. If you wanted a different conformation of the structure, you're always welcome to draw it in a conformation that works for you. In my opinion, that's not as pretty. Cooper? Oh, so like now you have this position. Yeah. That's a good question. I'm not sure that I've considered that before. I mean, yeah, in theory, that does seem logical. Actually, if we were to think about where is the next most acidic hydrogen, we might actually say that it's down here. Because at this position, it can be in resonance with the alpha carbon and then also with the carbonyl. But having that increased resonance might also mean increased stability and less reactive. But generally, we don't show reactions that go beyond that first step. Yeah, great question. All right, let's make things a little bit more complicated. You okay if I erase this? Why react the same two molecules together? What if I want to react two different molecules? We call this the crossed Aldol reaction. We could call it cross Aldol addition or cross Aldol condensation, depending on what we want to run. And not to say that one is better than the other, but in general, we will do a lot more aldol condensation than we will aldol addition. So for all of these four examples, you could show both the aldol addition and the aldol condensation products that form. I want to focus just on the aldol condensation products. So this, in this reaction, what we're doing is we're taking two different reagents. I've chosen that they are an aldehyde and a ketone, but this could be two different ketones. This could be two different aldehydes. And we're going to mix them with sodium hydroxide. Here's where the issue is. Which compound is the nucleophile? Either one. Which compound, so I should have said, which compound can be the nucleophile? Either one. Which compound can be the electrophile? Either one. So the cross-aldol dilemma is that we get four different products. What happens? We can say this is compound A and this is compound B. What happens if A attacks A? What happens if A attacks B? If A can be the nucleophile, that means we have the possibility of A attacking another equivalence of A and of A attacking an equivalence of B. But if B can be the nucleophile, then we might see B attack B. Once again, I'm sorry, but there are a lot of correct ways to draw the conformations for these structures. You just need to be paying attention to the functionality. Conjugated carbonyl, even if it has a bit of a different orientation. What's the last possibility? B attacks A. And I know the space on that sheet might be weird to kind of have those all stacked. So you might need to have them kind of spread out across that page so that you have enough space for them all. Yeah. In theory, maybe not to the same extent though. Exactly. So it might be that one of these is the most major product. And sorry, just for some context, I'm showing you guys some of the other conformations that you can draw these. The other conformations you can draw these in. More than one conformation. I want you to kind of be familiar with them being horizontal conjugated carbonyls and vertical horizontal vertical conjugated carbonyls. So yeah, we could probably run this reaction and then find that B attacking A gives us 60% of the yield. B attacking B gives us 10% of the yield. So does A attacking A gives 10% of the yield. And I lost track of where my numbers were. So the rest is here. 20. Thank you. Ultimately, not for us to decide. Instead, we're going to look at the bottom half of this worksheet that says how we can control conditions for cross-aldol reactions. You guys are okay if I erase this side? I feel like we're flying through the boards today. Oh, you know what? Before we do these bottom three, I think what I want to have you guys do is retrosynthesize. So I want to give you two structures and have you tell me what they came from. This one will be from just one structure, intramolecular reaction. Sorry. Nope. No, these problems are actually not on the worksheet. So these are both cross Aldol condensation problems. And I want you to tell me what starting material could get you there. Let's not focus so much on the reagent, like the catalyst that you're using to run this, but just tell me the starting materials that are needed to get you here. Good. Think about that tip we had earlier and how can you use that backwards? See a lot of people labeling alpha and beta. That's exactly what I want to see. Yes. Not quite. This is alpha, and this is beta. 1, 2, 3, 4 attacks 5. But I want to have 1, 2, 3, 4, 5. What? 1, 2, 3, 4, 5, 6. Yeah, I want to have 1 attack 6. Or the way you've numbered it, 6 attack 5. I want to make a 6-membered ring. Your option would work at making a 5-membered ring. No. So actually, this would be an alpha hydroxycarbonyl.
Okay.
And we saw earlier, you missed it, is that we can form beta hydroxycarbonyls. And
Okay.
so there is actually a precursor to this, an intermediate, that is a beta hydroxycarbonyl. But in the same way that you cleaved, actually this is not your beta carbon. That's carbonyl alpha. And then alpha attacks beta. There's beta. You're going to do the same thing. Here's alpha, here's beta. You're going to cleave that bond. Close. You're actually short. You're short by a carbon, right? Because you know you have a 6-membered ring.
Oh, so it would be a ketone.
There you go.
Okay.
Yep. Alpha attacks beta. So that's 1, 2, 3, 4, 5. Attack 6. Good. Perfect.
I'm sorry.
That's okay. That is an aldehyde, yeah. This is going to come from an intramolecular reaction. So you should have just one reagent here that has 2 carbonyls inside of itself. Remember our tip earlier was the beta carbon of the electrophile was a carbonyl carbon. Here's your beta. That needs to be a carbonyl. Here's a beta. That needs to be a carbonyl. You're close here, but you actually don't have enough carbons. If this is alpha, which we need to have attack beta, that means that carbon 1 attacks carbon 6. Here you've only got 5 carbons. So all you need to do is change one of your H's. Yep. So if that's a CH3, alpha attacks beta, makes your 6-membered ring. You saw earlier how I put my 2 equivalences up there, and I erased the O and I drew my double bond?
Yeah.
Reverse that. Erase the double bond and put in an O. Did you guys hear that?
No.
Yeah, actually, you're doing it. Earlier, I put my 2 equivalences together. I just set 2 equivalences next to each other. I erased the O, and I drew the double bond between alpha and beta. Reverse that, break the double bond, and put in an O.
Okay.
Close. You have flipped alpha. You've kind of flipped like which carbonyl should be attacking which position. So this is the carbonyl that's preserved. Is that correct?
Mm-hmm.
The carbonyl that is preserved is the nucleophilic carbonyl, but this carbonyl can't be a nucleophile. This carbonyl has no alpha hydrogens. So this alpha carbon belonged to this carbonyl. The alpha carbon always came from the carbonyl that we see. That alpha carbon attacked this beta carbon. This beta carbon used to be a carbonyl. So you should have a structure here where beta is a carbonyl carbon. One thing that you can do is copy this, erase the double bond. Those are going to be your 2 groups. Does that make sense?
Mm-hmm.
Erase that alpha beta double bond. Now make beta a carbonyl, and you're done. Move them away from each other so you don't mistake anything. Yep. Yep.
Correct.
Yes.
This is right?
Yes.
And maybe swapped it all?
Nope.
There's only one possible?
That's the only way that you can get to what we have here. Perfect. Perfect. Okay, who haven't I checked yet? Good. Good. Nira, did I check you yet? Close. You're on the right track. Should we go through it together? All right. First of all, label your functional group. There are a lot of alpha and beta positions here, but there's really one alpha and beta that's of interest. That's the alpha beta double bond. The alpha beta unsaturated part of the carbonyl. Here's my other alpha beta unsaturated. Remember the tip from earlier. The beta carbon comes from the electrophile carbonyl carbon. So when you are retrosynthesizing, I want to see the beta carbon as a carbonyl. Can you tell me what carbonyl means? Because this is a very important part. Huh? CO double bond. Good. Carbonyl, acyl, all that fun stuff. Okay, so beta needs to be a carbonyl. Here's what I'm going to do. I'm going to redraw this structure. And I'll do such a good job doing it. And then I'm going to erase the alpha beta double bond because that is the bond I'm trying to form through this reaction. I will make beta a carbonyl, and I'm done. Erase that CC double bond, make beta the carbonyl, and it's over. I'm going to redraw this because it looks a little sloppy as is. Didn't get any better. Wow, I'm on a roll tonight. We'll do the same thing up here. I'll redraw my structure. I'll erase my CC double bond, and I'll make beta a carbonyl. Now that's kind of an odd conformation for that molecule. Here's another conformation that looks a little less odd, but this is no less correct. 100% correct. I've noticed a lot of you trying to map using A and B, but also count carbons to make sure you're not losing anything. So if we say alpha attacks beta, beta 1, 2, 3, 4, and I'm back to alpha. Alpha attacks beta, beta 1, 2, 3, 4, and I'm back to alpha. Or again, this conformation, but with a little bit more exaggeration in that alpha to beta distance. That looks good. Another way that you can break this backwards, erase that CC double bond, and just draw that carbonyl off in a different direction. So it's not kind of cluttering the space that you're drawing in. So many good ways to do this. Here is the most important part. If you have not written this down in your notebook, don't wait. It's not going to make sense unless you come back and practice it and practice it and practice it. But once you recognize that the beta carbon of that functional group used to be a carbonyl carbon, you solve the retrosynthesis in seconds, especially with these condensation products. All right, so quickly, before I let you have a break, those 3 points. How can I control these cross-aldol reactions? The first one is limit the number of hydrogen, alpha hydrogen possibilities. Or in other words, limit the number of carbons that can become a nucleophile. If you limit which if you limit which compound can be a nucleophile, you limit how many crossed products you can make. Can this structure be a nucleophile? The answer to that question, or a way to answer that question, is to ask, does it have alpha hydrogens? Because if it has alpha hydrogens, it can be a nucleophile. This has alpha hydrogens, so it can be a nucleophile. That means whatever I react this with should not have alpha hydrogens. That way, it cannot be a nucleophile. Can anybody give me a structure that does not have alpha hydrogens? No, go give me yours too. Formaldehyde. So like a quaternary carbon. How about ditert-butyl ketone? There's another one that works really well. Benzaldehyde. Oh man, even benzophenone. All electrophiles, never nucleophiles. To be fair, there is still some competition because this ketone is the only nucleophile, but it can also still be an electrophile. So I don't get AA, AB, BA, BB, but I still can get AA and AB. So there's less combinations, but still multiple combinations. Do you guys feel like this makes sense? The other way that you can control cross-aldol reactions is to promote electrophilicity. I phrased it here as promote selective reactivity. That is, whatever your nucleophile will be, make sure that your electrophile is just more electrophilic than the nucleophile is. In general, that means taking something like a ketone and reacting it with something like an aldehyde. And the best aldehyde to do this would be formaldehyde. Formaldehyde has the strongest partial positive. More partial positive on the aldehyde, less partial positive on the ketone. So it's less likely that the ketone acts as the electrophile. It's more likely that the aldehyde acts as the electrophile. And you can combine these two features. You can limit alpha hydrogens and you can promote electrophilicity. We saw that here, where formaldehyde cannot be a nucleophile and it's more electrophilic. That's really going to limit crossed products. But something like ditert-butyl ketone, that's actually less electrophilic because of all that steric strain. So you don't have as good of a chance of promoting that electrophilicity with this combination. Sure, there's only one nucleophile, but that nucleophile is also the better electrophile. The last tip here, complete enolization. And honestly, this is what you should use most of the time. Don't leave it to chance with a kinetic base. Sorry, don't leave it to chance with a thermodynamic base. Don't create a small amount of nucleophile from this reagent that can then attack the remaining of that reagent that is still an electrophile. Take whatever compound you want to have serve as your nucleophile and turn it completely into an enolate. Do you guys remember LDA? It is not the same as LAH. LAH, strong reducing agent. LDA is a strong base, a strong kinetic base, and it does 100% enolization. It will take whatever carbonyl you give, and it will turn every molecule into the enolate. When we do these reactions with sodium hydroxide, or even tert butoxide, or ethoxide, methoxide, we get, do you guys remember the numbers? We get like 1% of the carbonyl is turned into a nucleophile. Up to 10% of the sample is turned into a nucleophile. You get a small amount of the compound as a nucleophile, and a lot of it sitting around still as an electrophile. LDA doesn't leave any of it as an electrophile. 100% enolization. Then introduce whatever you want. Now you don't have to limit alpha hydrogen possibilities. The next thing that comes in will only be the electrophile because you have just 100% created a nucleophile. You don't have to limit nucleophilic capacity. You don't need to promote electrophilicity. So we add something like this, something that has alpha hydrogens and would technically be a less reactive electrophile, but it doesn't matter because step 1 completely created a nucleophile, and now I'm just adding in that new electrophile. All right, I want you guys to have a quick break. If you want to, I recommend making some predictions about what aldol addition or aldol condensation products these can make. But we have some more reactions to look at in the second half of the class, so I want to make sure we get on to those. So let's take 5 minutes. Let's be back here on 6:18. Great. All is well in the world of active chemistry. Last week I gave a talk to the college, and I knew that I wanted to record it, so I looked into some like wireless microphones and found some cheap ones because like typically it's my laptop mic that picks up my audio. Yeah, when I walk away from it, my voice gets quiet. And then sometimes I get too close and my voice gets really loud. So when I gave my talk, I didn't want that to happen. I didn't want to like be glued to my laptop and not be able to walk away because it wouldn't pick it up. Turns out there was a microphone in the room too, and so I stayed with my laptop anyways. But so I bought this for that. That was last week Monday. I had a Gen Chem lecture Monday morning before this talk, so I was like, I should practice with it. Should make sure that it works. I started my recording. I have my little app has a little window that pops up that shows me the camera footage. And it's got a tiny little microphone icon that has a bar that moves up and down when it picks up me speaking. And I was looking at it. I've had this happen before where I record an entire lecture and for whatever reason, the microphone wasn't turned on. And so I was looking at it and I was like, oh, I don't think it's recording the audio. I'm not sure what's going on. So in front of my class, I'm like embarrassed. I have this little microphone strapped to my lapel and I look silly. So I was like, guys, I'm nervous that it's not recording. So I stopped the recording and I started it over. And I'm still trying to figure out like where's the best place for it. So I stopped the recording, I started it over, and I realized the mic wasn't on. There's a power button on the mic. And so sure enough, like later I went back to listen, no audio, because the mic wasn't on. But I ran into another problem. My laptop wasn't fully charged. And that's fine normally, because I just plug in my laptop. But this has the receiver from the microphone plugged into one of the two USB-C ports in my laptop. And it's like long, so it blocks the other USB-C port. So I couldn't charge at the same time. But the receiver has a USB-C port of its own. So I plugged my charger into the receiver, and it started charging my laptop through the receiver. Okay, that's a lot of energy going through a tiny little, like, $10 receiver. And so the receiver started getting really hot. And I was nervous that I was going to kill it before I could even use it that night at my talk. So I was like, I'd unplug it, give it some time to cool off, and then plug it back in before the laptop would die. Oh my goodness, it was such a pain. When I plugged it in the first time and then unplugged it because it was getting hot, for whatever reason, my computer had some like mix-up communicating with my camera. Because this communicates by not Wi-Fi. I think it's cellular data. It always says it disconnects from Wi-Fi to improve the connection. It was communicating through there. It had some disruption to that. And so my recording on my laptop got paused and I didn't notice it. And I never pressed play again. So it missed like 10 minutes of me finishing a problem that we were solving and then me talking about the schedule and then me putting them on break. And so I pressed play again after the break, but I'd lost like 10 minutes. I was so upset. Like I figured out a system. It worked for me. Okay, whatever. My audio gets cut in and out because I walk away. Who cares? And now I'm like all flustered and I'm learning this new thing and it's embarrassing. And what am I, a social media influencer? Like, what answer do you have for problem 3? I know, right? My voice is loud, yes. No, this mic doesn't amplify. No, it just goes right there. It's not, there's no speakers in here. That's just my voice. Everyone says that. People will walk past my lab and they're like, "Hi, John, I heard you from the stairwell." Okay, great. Come on in, we're talking about chemistry today. So this receiver draws power from my laptop. It kills my laptop faster. And it's already it already draws a lot of battery. My phone is recording for 2 hours straight. That takes a lot of battery power. My laptop is recording for 2 hours straight. That takes a lot of battery power. So now, if I want to use my mic, I have to come in with the mic fully charged, my phone fully charged, my laptop fully charged. Like, goodness gracious, like this is a job in and of itself. Okay, anybody interested to see the products from the reactions that we did there? Okay, understandable. I'm not sure that I'll be able to make it very pretty. I'm just going to kind of clear some space here. Let's do this first one. Can I label this? 1, 2, 3, 4, 5, 6. And that'll allow me to make a little bit more space over here so they look more clear. Now, I'm going to ignore, in that first problem, I'm going to ignore all of the cross Aldol condensations that could happen. And I said I'd ignore it, and then I just drew it. So that's the possibility if that nucleophile attacks itself. But the possibility that that nucleophile attacks electrophile number 1, not 50-50. Alpha attacks beta. The electrophile was intended to be the beta carbon. Beta is a CH2. Nice. That's a cool structure. Number 2. You guys see it, right? Formaldehyde. Just a 1-carbon carbonyl, so I get this. The only thing I change is now I've got these tert-butyl groups on either side. Looks a little bit less cute. Number 3. To be fair, there are actually 2 stereoisomers, the E and the Z alkene, that could possibly form. It's most likely going to form the lower energy stereoisomer. That'd be the E alkene. Number 4, where it becomes a ketone. Are you guys seeing the pattern? Seeing the repetition? We get the same nucleophile attacking different electrophiles. In problem number 5, this actually depends. If we ran a reaction with something small like sodium hydroxide, then the thermodynamic enolate forms, and we get our alpha-beta unsaturated carbonyl at a certain position. But if I run this with something big and bulky, like tert-butoxide, the kinetic base forms, the kinetic enolate forms, and so I can get structural isomers from this reaction just based on what base I want to use. Are you guys okay with that idea? Structural isomers based on the sterics of the base. It's actually not new. We did that in E2 reactions back in OChem 1. All right, now here, my nucleophile is only this position, so I have no chance of crossed reactions anymore. Alpha attacks beta, and what I gave us was beta having a tert-butyl and a methyl. Once again, there are stereoisomers that can form here. I'm not necessarily asking you to be able to predict which stereoisomer is more likely to form. Sometimes they can be a little bit hard to judge, but if we say that tert-butyl is a big bulky group, it's probably going to have more steric strain, being closer to that phenyl group. So the E alkene is probably more favored. 2 stereoisomers. Do you know how I normally get around trying not to trick you about what stereoisomer is more likely to form? Just give you a symmetric electrophile. I give you something with 2 groups that are the same on either side, so that you don't have to guess whether it's the E or the Z alkene that forms. So that's not what I'm trying to test you on. I'm trying to test that you can find the major product. We've already talked about stability of the alkenes back in OChem 1, so it is an underlying knowledge.
Why is this different if you use NaOH?
If we use NaOH, 10% of this aldehyde will become a nucleophile. 90% stays electrophilic aldehyde. That's where I can have A attack A and A attack B. If I use something like sodium hydroxide, I get that cross aldol issue. If I use LDA, there is no potential of A attacking itself because there's no electrophile left. It's all been turned into a nucleophile. And by the time I add B, I don't have sodium hydroxide sitting around. There's no chance of B turning into a nucleophile. Tert butoxide is still bad at giving enolates. It doesn't do full enolization. Sodium hydroxide, about 10% becomes a nucleophile. Tert butoxide, about 10% becomes a nucleophile. So you still have that issue of A attacking itself, of B attacking itself. But with LDA, 100% enolization every time. But it's a kinetic base, so you have that regio control. You'll always get the less substituted enolate. Does it feel hard to get those gears moving again after Thanksgiving break? I could feel that at 10 a.m. yesterday in my Gen Chem 1 class. They were working hard to get those gears moving, and it feels like it's been a long time since we talked about kinetic and thermodynamic bases. All right, what happened to this? On the back side of this sheet, we are moving on to some other types of condensation reactions. Is there a part of the board you guys are okay with me clearing? Maybe the right-hand side? Okay. Maybe I'll leave it for a little bit, but I'll clear this side. Claisen. Have you guys heard that name before? Where? In lab. For what? Yeah, the Claisen head, the Claisen adapter is this kind of like U-shaped piece of glassware. It's actually a little bit more offset on one side. When I was in chemistry in college, I used that as the H in my name, and I would take glassware to spell out my name, John. It's a good H. That's the Claisen adapter, named for the same guy that the Claisen condensation reactions are named after. I want to point out something that differentiates Aldol condensation from Claisen condensation. Aldol condensations have aldehyde or ketone starting materials. Claisen condensations have ester starting materials. You'll notice that we didn't do any examples with esters yet, despite the fact that we said they would be an important part of this section. I don't know if I said that actually. I might be lying. They will be an important part of this section. They get their own name. So that first example, let's take two equivalences of this compound. Do you guys know this compound? What's this? Can you name it? No, not a keto ester. There's only one carbonyl. It's an ester. Ethyl acetate. Always name the alkyl group of the ester linkage, then name the carbonyl chain. This is a 2-carbon carbonyl, so it gets asa. It's an ester, so it ends with 8, or typically O8. Ethyl acetate. Another name for it would be the more systematic name. Ethyl ethanoate. Yep. When this reacts with a base, like sodium hydroxide, it becomes saponified. It goes back to a carboxylate and an alcohol. So we cannot use sodium hydroxide. What do we use? Aldehyde is a choice, but we'll actually get to that in a minute. Ethoxide. We use a base that matches the ester linkage. Because I have an ethyl chain, I want to use ethoxide as my base. Here's the product that I get. Do you know this compound? It's not my favorite. Don't tease me. It's not funny. What is it, Jordan? Good. Ethyl acetoacetate. We have just made the precursor to the compound, we've just made the precursor to the alpha alkylation reactions. Yeah, we used this when we were adding new carbon groups down here. So we have just added a step into our sequence. We can use Claisen condensation to make what functional group is that? Beta keto ester. Although that is a very specific name, it's not always going to be a ketone. Good. So we can call it a beta carbonyl or a beta acyl carbonyl. Oops. Beta carbonyl ester, beta carbonyl carbonyl, beta carbonyl acyl. No, beta acyl carbonyl is probably the other best one. In our aldol condensation reactions, water condensed. Water was formed and precipitated from the molecules. What is condensing here? Sorry, that was so vague. Ethanol, is that what you're going to say? Plus our byproduct, ethanol. Ethoxide serves as a catalyst. Why does the bond break? Yeah. There were two equivalences of esters. One of the esters has kicked off its ester linkage. We'll look at the mechanism for this as well, but I think what you'd like to see here, Killian, is this is our intermediate. Alpha, the alpha carbon of one of the esters, has attacked beta, the carbonyl carbon of the second equivalence. This is a tetrahedral intermediate. It should look very reminiscent of the intermediates when we use dibol. Take dibol with an acid chloride, and you create this kind of intermediate, and then you kick off the chlorine. Use dibol with the anhydride. You create this intermediate, and you kick off a carboxylate. Dibol with an amide, and then you hydrolyze and kick off the nitrogen. So we're going to look at the mechanism more later, but we reform a carbonyl, and we kick off that leaving group. This is unique to the ester, this ability to kick off a leaving group. The ketone cannot do this. The aldehyde cannot do this. The ketone and aldehyde don't have groups that willingly walk away with carbons. Hydrogens don't leave with carbons. Carbons don't leave, oh, sorry, that sounded weird. Hydrogens don't leave with electrons. I think the whole time I said it, I was saying it wrong. Hydrogens don't leave with electrons. Carbons don't leave with electrons, but oxygen groups, those can leave with electrons. So our condensation gives us a beta keto ester. then we have what's called the Deichmann condensation. Now this is where somebody should have been real mad, and they weren't. And I wanted, I guess I didn't point it out very well. I wanted to point out you don't need to use ethyl esters for this, although it is common. No, they're not necessarily more stable. All right, this carbon chain is, I'm bad at counting. 1, 2, 3, 4, 5, 6, 7 carbons long. Yeah, I should have known that. A Deichmann condensation is an intramolecular Claisen condensation. So either Claisen should have gotten really mad about that, because that's just his reaction, but inside of one molecule. Or Deichmann should have gotten mad. I don't know who came up with their reaction first. This is where alpha, the alpha carbon to one of the esters, attacks beta, the carbonyl of the other ester, inside of the same compound. Alpha attacks beta, beta 1, 2, 3, 4, back to alpha. So if you're going to draw a ring, this is now a 6-membered ring. Beta will be inside of that ring. Alpha to beta makes the ring. The carbonyl that is acting as the nucleophile, that will stay outside of the ring. Once again, my base, ethoxide. Wow, that's a very pretty picture, but not what I want to see. Interesting. Fun way to make a ring. Kind of a horrendous molecule to start with. A lot of carbons going on. We don't need to specify that it's run in heat, no. Alcohol on wax. Where do you see an alcohol being added? Ethanol minus is not an alcohol. Deichmann condensation's generally pretty easy. There is an interesting feature of this. The beta keto ester, more acidic or less acidic than the ester starting material. The product, beta keto ester, more acidic or less acidic than the ester starting material. More acidic, why? Increased resonance, more carbonyls. Which means that these reactions require an acid workup. For now, that's not always shown. I may make that different in coming semesters, and I may start showing that this needs an aqueous workup. Whew, just like, when will I get the time to do that? Why does this need an aqueous workup? Because this base is a catalyst. By the time I form this product, I have kicked off an equivalence of ethanol, that is the alpha hydrogen of one of the esters and the ethyl ester of the other ester. They leave as ethanol. And I reform my catalyst now in an even more acidic environment. That compound doesn't stay as it is. That compound gets deprotonated. And now needs to go through some sort of aqueous workup, some acid workup, in order to truly isolate the beta keto ester. Don't hydrolyze it. Don't add H3O plus and heat, or you will turn this into a carboxylic acid and then run decarboxylation. A useful thing if you wanted to maybe make cyclohexanone, you could cleave off that one carbon of the ester and leave yourself with a ketone, but not useful if you want to use that beta keto ester. I don't always require this, but I will say this was where I lost points in one of my OCHEM 2 exams in college, and I went to my professor crying. No, I'm just kidding, but she acted like I was crying. And I was like, I'm confused. Why are you saying I missed a step when all I did was not deprotonate and reprotonate the compound? Why would I show that I get my product, I change my product, and I get my product back? And she said, because that is what's happening. It's in a basic condition, and that is a more acidic hydrogen, so of course it gets deprotonated. I do want you to pay attention, because sometimes I have these questions where I need you to show a mechanism to a certain phase, to a certain point, and you need to pay attention to the charge that's on there. It may mean going a step further than what you think. So I want to explore this a little bit more, this concept of how the substitution can actually make an impact. The first Deichmann condensation that we looked at, very symmetric, correct? It wouldn't matter which alpha carbon I had said attacked which beta carbon, it would have been the same. But now let's consider the alpha on the left attacking what will be beta on the right, and the alpha on the right attacking what will be beta on the left. Correct. Ethoxide is the catalyst. Methoxide, propoxide, isopropoxide. If you use the wrong base, then you will transesterify. That's the big problem. You want to end up with just ethyl esters, not methyl esters. Correct. Your base, the catalyst, matches your ester linkage. All right, if the green alpha attacks the green beta, we get this product. Oops, sorry. Boop. That green beta has an adjacent alpha carbon with a methyl group coming off of it. And because we haven't done an aqueous workup yet, this sits as its enolate form until the acid workup. Are you guys okay with that? On the other side, where my blue alpha attacks my blue beta, can I deprotonate? This alpha position has a hydrogen, and so ethoxide deprotonates. I have to undo that with an acid workup. This alpha position deprotonates. It's stable as this enolate. I have to work to undo that. Can this product deprotonate? No. which means it's actually not stable. And this product can go through a reverse reaction, which means that this is never isolated. Because if it does go through a reverse reaction, then there's a chance that this reaction happens instead, and this reaction doesn't reverse. There's nothing to reprotonate this. That's one of the most significant parts of how the alpha acidity impacts which product is made. Yes, it's an asymmetric Deichmann condensation, and yet there's one product that's formed. We say that this falls into an energy well, a thermodynamic well. It's very hard for that reverse reaction to proceed, whereas this one never falls into that same energy well. So before we leave, the last few problems on here are things that you can take home. The third one on this list, I wanted to show you cross Claisen control. Just like how we looked at the cross Aldol control, we said that we could limit alpha hydrogen positions, promote reactivity of an electrophile, but predominantly just use complete enolization. And we'll do the same thing with Claisen reactions. First, introduce LDA. And then second, introduce whatever whatever ester you want to introduce. Let's introduce methyl formate. Formate, remember, is both an aldehyde and an ester. So instead of having a carbon chain, instead of having a beta keto ester, I'll have a hydrogen coming off of my product. And I get a cross beta keto ester, or in this case, a beta aldehyde ester, a beta acyl ester. This becomes the only nucleophile. This behaves as the only electrophile. I don't have this possibility of one attacking the other. I can control my cross Claisen reactions. Are you guys okay with the fact that we didn't go through an example where we have 4 different cross Claisen products that could form? We know how to control them now. Add LDA, take one of those compounds and just make it the only nucleophile. It can't attack itself, and then introduce the electrophile. I'd encourage you to take a stab at these next ones. These are other crossed reactions where instead of having aldehyde with aldehyde, aldehyde with ketone, ketone with aldehyde, or having ester with ester, these next 3 reactions take esters, aldehydes, and ketones and put them all together. So you get this kind of hybrid Aldol reaction, Claisen reaction. You'll notice that some of them are beta hydroxy esters rather than beta hydroxy aldehydes or ketones. It's like an Aldol reaction, but with an ester. Some of them are alpha beta unsaturated esters instead of alpha beta unsaturated ketones or aldehydes. So play around with the tools that you already have about retrosynthesizing these products and figure out what would be a good step. First LDA, second what compound in order to make those. We'll start off class Thursday with that. We have just like 2 more reactions I'll bring a worksheet for and some mechanisms. All right? Then we're done. Okay, thank you guys for your time. Have a good night.